Okay, so it's a great pleasure to introduce our first speaker, Dries from NYU, who's going to tell us about quantum optimal transport through periodic driving.
So as announced, I'll speak about quantum optimal transport with periodic driving. And this might be a little bit off topic, but I've really tried to put some Floquet or periodic driving in my talk. This wasn't easy, mostly because all of the things I've done on Floquet and everything I know about Floquet, I've learned from people that are sitting in this room. So I felt like I should talk about something else. And well, I hope it will become clear during my talk what I will try to speak about. Basically, one motivation for my talk is the following. It's that imagine, I mean, all of us in one way or the other probably work on quantum simulation or artificial quantum matter or quantum computing for that matter. And one question you could pose, which is maybe just a motivation for this talk, is that what can we do with small noisy quantum computers, right? We've all been asking this question. Everyone's building larger and larger and larger quantum devices, but it's been a challenge to make it less and less and less noisy at the same time. And so we've come up with some ideas of what one could possibly do. That is something like optimization or quantum chemistry or quantum machine learning. All fancy words. But if you look at any of these applications, the kind of theme throughout is basically that we are going to try to use these quantum computers by supplementing them with classical computing. That is by trying to optimize some variational parameters in this approximate optimization algorithm in this VQE, or there's a bunch of unknown variational parameters in these machine learning problems. So that's the idea. We have this quantum processor or quantum device. You can maybe do some measurements and feedback control. And you're trying to kind of control this quantum device as good as possible. But now I'm getting to the point, basically, is that efficient control of these quantum systems is therefore the key, right? When we go from, I have a universal quantum algorithm like Shor's algorithm, well, basically, I pretty much know what the circuit is I'm supposed to run. Any of these NISQ applications, well, you don't know what the circuit is that you're supposed to run, right? The whole point is to try to find variationally somehow the smallest possible circuit that prepares the state that you like. And in one result here with also Marin, who's here, we've basically, I think, shown in this paper pretty clearly, and there's been some more mathematical works also after this paper, that general efficient control of a quantum system is not possible. And I mean, I don't think this is a surprising statement altogether. It's basically exponentially hard to find good controls in general. So this begs the question, well, if you're trying to solve this to solve quantum chemistry, or you're trying to do this to solve some hard optimization problem, aren't you just replacing the hard problem by an harder problem? That is the harder problem of controlling your quantum computer. In general, yes. So now the question is, can we do something about this, right? Can we maybe in some regime come up with some way to come up with good controls? And I'd say one intuition one can take is, let's go back to how we control classical things, which is that how do we control car engines or the engine of something else? And well, basically we've learned a great deal of stuff from thermodynamics, right? And at the end of the day, information processing and thermodynamics, there's this strong connection between them. So you can ask, well, why can we make, I'm not trying to do optimal control when I'm trying to make a power plant, right? I'm not trying to variationally optimize the parameters of my engine. Well, typically the way we go about generating some device that can generate some power is through, well, in this example I'm showing, it's a Carnot cycle. So we have some thermodynamic cycle which works and has great efficiency, say maximal efficiency in the adiabatic limit, right? And So the key thing I'm trying to convey here is that basically we have some universal process that can do what we like to do. It's basically the adiabatic process. And the same thing is true for quantum computing. For many of these problems that I've shown, actually probably all of them, there is a very easy way to have an algorithm that would actually prepare the ground state of your molecule, find the ground state in your optimization problem. It's the adiabatic process. It's some process where you basically connect the state that you're trying to find adiabatically with some state that's very easy to prepare. But there's of course also an immediate link with thermodynamics, again, in the sense that, well, just like in thermodynamics, this adiabatic process, well, in order for it to work, it needs to be adiabatic, right? And if it's not adiabatic, we lose efficiency. And the same thing is true in this Carnot cycle, right? A typical actual engine works at a much lower efficiency than it could work if you were to do it adiabatically. And the problem is a little bit that if you really do it adiabatically, then you're generating no power, right? Because you need to do it infinitely slowly. So you generate a super efficient process, but if you ask how much power is coming out of your engine, well, zero. How much power is coming out of your quantum computer? How much information are you processing? Well, zero, because you need to do it infinitely slowly. So now this question is, well, in practice, of course, just like in the engine, you can do it at a finite speed and lose some efficiency, right? And the same thing is true on the adiabatic process. The only problem is that for most of the problems we're interested in, well, you can only do it a little bit slower than infinitely slowly because the gaps in this problem are typically exponentially small. So the question is, can we come up with some kind of procedure, some method that can try to do this, take this adiabatic process and sort of speed it up? And that's what I'm gonna try to talk about. How can we speed up in general adiabatic processes? That's the first part of the talk. And then the next part is basically how can we use Floquet, just to be on topic here. How can we use Floquet to do this? So this is my pedagogical introduction to this subject. So when we think about non-adiabatic processes, I think it always helps to focus on this very simple example. So let's consider the example where I have a particle. It has this very simple Hamiltonian p squared, and then it has a potential v. And I'm drawing this potential here. Maybe, you know, it's like some Gaussian laser beam, and there's a particle trapped in it in the bottom, right? That's this kind of dashed line over here. So think of this dashed line as this potential v of x minus lambda of t. And lambda of t is my control parameter. So that's the thing, as an experimentalist, I can change as a function of time. And what I'm gonna try to do is that I'm gonna try to move this atom around as quickly as possible. And I mean, this is a very simple task, but actually these days it's even becoming relevant in real quantum simulators because people are making these Rydberg atom quantum simulators where actually moving around the atoms is a way to do fast gates. So let's look at this process in a little bit more detail and try to understand what in this process here is the diabatic transition. So I'd advocate it's actually useful to go to the moving frame. So do a unitary transformation u of lambda that actually moves you to the moving frame that's co-moving with lambda. So I do this. Well, since I still want the wave function psi to obey the Schrödinger equation, I substitute this unitary u, this transformation in my Schrödinger equation. And it basically means that the system has an effective Hamiltonian, which, well, what does it look like? Very simple. It's the unitary transformation of this Hamiltonian h. But if lambda is not static, but lambda depends on time, there's one extra term which just comes from this time derivative here, which is basically the time derivative of u of lambda times u dagger lambda, and this I comes from here, right? So that should be straightforward. So in this particular case, what is u of lambda, right? Just for this particular example. Well, for this particular example, let's say u of lambda is just the unitary transformation that always moves this tweezer to a fixed point. Let's say this fixed point is just the origin of my coordinate frame. So then Well, it basically means that whatever lambda of t was, I have to translate my tweezer back to the original position. So this unitary transformation is the generator of well, it's generated by translations, right? So the generator of translations is the momentum operator. So basically that means that if I work out this kind of term over here, well, since I want to translate the tweezer back, I have to apply p e to the ip delta lambda, right? So if I take this time derivative and cancel this I, well, I basically get a term which is the velocity of my tweezer, lambda dot, times the momentum operator, right? Very simple. And to make this a little bit more apparent, you could sort of just complete the square over here. So you get a p minus lambda dot squared, right? And then I can do just a gauge transformation to remove this kind of thing and turn it into a potential, right? And so after this transformation, well, this extra small gauge transformation, I see something that becomes very apparent. I get the mass, which came from completing the square, times the second derivative of lambda times x. Well, and so I guess everyone now sees what this is. It means that in the moving frame, my Hamiltonian is just the original Hamiltonian, but at a fixed position times a force. Well, which force? Well, a linear potential, that's just an actual constant force, right? And the force is just equal to the mass times the acceleration. Well, yeah, it's just a pseudo force or the non-inertial force that you basically feel because you're in a frame that's accelerating, possibly, right? So in this frame, that's not an inertial frame, your particle feels a force. Everyone knows this. The force is proportional to the mass times the acceleration. And that's what I'm plotting over here. Okay, but you see, this we all understand. And I mean, I guess Einstein taught us a hell of a lot about elevators that are moving and how you feel acceleration in this elevator. But this is entirely general, right? So I would say in general, I could have a time-dependent Hamiltonian, which depends on a bunch of parameters. I'm gonna conveniently call this object the derivative of u with respect to lambda a gauge potential. And in this moving frame, I see a Hamiltonian, which is the original one transformed into this moving frame, and some gauge potential times the velocity. Okay, so this is just explaining what these non-adiabatic forces are. And so now what is the idea? You might already kind of get it by now, is that in order to avoid that we have any diabatic transitions at all, right? In order to avoid that this particle does not get accelerated by the pseudo force, so stays in equilibrium in the moving frame, well, I have to cancel the pseudo force, right? Imagine again in my elevator experiment, if I accelerate the elevator, but imagine you're also a charged particle, a lot of things to imagine. Then you see that basically you could, for example, if this was a capacitor, charge the capacitor in such a way that basically the electrical force that you feel exactly compensates the force from the accelerating elevator. Or you could use gravity to compensate for the acceleration. And if you do that, then you will stay perfectly in equilibrium. So the very, very simple idea of this counterdiabatic driving is basically that, yeah, you can keep systems adiabatic. It's actually, in principle, not that hard. It just means that you have to cancel this, this pseudo force, which means you have to add lambda dot, the velocity, times this gauge operator. And if you still don't get it, the example I like to give a lot is this example of, imagine that you have a glass of water on a tray and I have to like bring it there very quickly. Well, if I do it, the universal process to do it is to hold it like this and go very slowly. And if you now do the same, but you try to do it very fast, then you feel a pseudo force, which means there's a force because you accelerate, which might tip the glass or make the water shake. But that's the thing, anyone who's ever done this, what do you do? If you have a very heavy tray with a lot of water or beers or whatever, and you want to very quickly deliver this, I mean, you just tilt this tray, right? When you move, you tilt it. Why do you tilt it? Well, because you're using gravity, you're using the gravitational force to compensate for the pseudo force on these glasses so that the glasses stay in equilibrium. And so we're gonna try to do this. but we're going to try to do this with quantum systems. And so one thing I want to also mention here is that one of the potential problems, and that's the big problem we'll try to sort of circumvent by Floke engineering, is that, well, you're going to have to add these terms to your Hamiltonian, right? And well, maybe these new terms, which I haven't shown you what they are, maybe these new terms, they're impossible to engineer. Like I don't have them in the lab. I don't have control over them in the lab. So this question comes about, if this is so easy to do, well, we have to ask the next question, that is that maybe these operators A are so complicated that I cannot get access to them. Well, in this paper over here, which was mainly about something else, also with Marin actually, we've proven that this is always possible actually. We've proven that there always exists a gauge transformation, so a unitary transformation here denoted as R, such that after applying this gauge transformation, this counterdiabatic operator can be generated out of the original operator just by modifying the controls. Or in slightly more mathematical terms, this object A of mu is in the semigroup generated by the original Hamiltonian, which basically means that you can always engineer this A out of modifying the original controls of the Hamiltonian, which means that this is really a way to do optimal quantum control, but in a two-step way. You can find first this generator of the diabatic excitations, this A of lambda or A of mu, and then you can try to basically remove it by doing an extra gauge transformation. And in effect, this example that I'm showing here is doing exactly that, because as I'd shown before, the actual operator that you get by going to the moving frame is just the velocity times the momentum, right? And if I want to cancel this and make everything adiabatic, well, I'm going to have to add to my Hamiltonian a term which is plus lambda dot times p, right? But at the end of the day, when I tilted the tray and used the gravitational force to compensate for it, I didn't do that. I added a force, right? I didn't add a momentum term, I added a force. Well, but you see, these two are related just by some simple unitary transformation. So that's, again, this statement over here. It doesn't just work for this simple particle. It doesn't just work for this glass and the force, but it works in general. There always exists a transformation such that this A can be turned back into the original Hamiltonian. And so now I think I've set the stage. This would be a way, in principle at least, to do optimal control of quantum systems. The name of the game is to do two things: find this A and find this R. And so let's first focus on sort of finding this gauge operator A in a many body system, because we're interested in many body systems, right? And so at the end of the day, finding this operator A is not that hard. So let's write down the matrix element of this gauge operator A between eigenstates of the Hamiltonian n and m. And I'm dropping the lambdas because, okay, n depends on which lambda I had, but then the slides become terrible. Well, I guess it's here, but so I have a matrix element n of A of lambda, but U is the unitary transformation that transports these eigenstates n to the position lambda. So there, these become n of lambda. So at the end of the day, the matrix elements of this object, they're just given by n of lambda and then the derivative of the mth eigenstate with respect to lambda. And now I can just use Hellman-Feynman theorem to basically turn the derivative of the eigenstate into the derivative with respect to the Hamiltonian. So after Hellman-Feynman, you basically just find this. The matrix elements of this gauge operator are given by matrix elements of this Hamiltonian. Basically, how do you control the Hamiltonian? What changes in the Hamiltonian divided by these energy denominators? And I mean, this just looks like a perturbation theory, right? It's just all the excitations in first order perturbation theory. That's also what it is. But so now, why is this so hard to find? Well, this is actually, it looks very easy, but of course most of you know, this is incredibly hard to find, not just because you have to diagonalize this Hamiltonian of the many-body system, but it has even a fundamental issue. The fundamental problem is that if you actually look at how large is this operator, right? So typically, how large are these matrix elements? Well, I have to check how large is the numerator and how large is the denominator, right? And now I can do a little bit of like random matrix theory. So if this was a random matrix, then the square of all these matrix elements should go down like 1 over the dimension. But since this is not the square, but just this, basically this goes down like the, this is small, 1 over the square root of the dimension of Hilbert space. So I could write this like e to the minus the entropy divided by 2. But this is the level spacing, right? When the energies are close together, this thing is dominated by these small denominators. Well, but this goes down like 1 over the dimension of your matrix. So exponentially small in the entropy. So basically this whole object, it actually grows exponentially in the microcanonical entropy, which basically means that, well, not a super surprising statement either, that it's exponentially hard to control chaotic quantum systems. If you want to try to control a chaotic quantum system or a state in the middle of the spectrum, this is exponentially hard. And this is trying to convey this. So if we look at the norm of this operator A as a function of system size, and we take an integrable or a free problem, then basically we find that the norm of this, well, it's at most polynomial, so that's good. That means it's sort of well defined. But in the chaotic limit, actually the norm of this object grows exponentially. So we need to, well, we need to somehow deal with these small denominators in some way that we can use this object. That's one thing. And two, actually, if we want to use this for quantum control, well, I better not need to be able to diagonalize my Hamiltonian, right? Because if I need to diagonalize my Hamiltonian to figure out what the good controls are, well, then why do I need a quantum computer, right? I solved the problem already. I diagonalized Hamiltonian. So basically, this is our trick. So we came up with this trick. It's not that complicated. So basically, this is the equation. So we want the matrix element of A in the energy eigenbasis. I can shuffle this around a bit. Basically, I can take these energy denominators to the left-hand side, right? If I do this, then En can go with N, Em can go with M. So this gives me a commutator of A with H. I get this matrix element here. So basically, that's this part. But you see, when N is equal to M, basically this object needs to be 0. So when N is M, actually, it's not that this is 0, it's that this is equal to the diagonal matrix element, which is the so-called Born-Oppenheimer force. And so you can write this whole thing as a matrix equation. So this is just an operator equation for this operator A. And it's kind of convenient since this is always diagonal. You can take another commutator with the Hamiltonian. So then this cancels this Born-Oppenheimer force because it's diagonal. And so then you just need to satisfy this equation. And now the simple thing is that it's not so hard to show that this equation you basically get by taking this object, take this left-hand side, the lambda H plus I O commutator with H, take the square of it, and if you trace it over the whole Hilbert space, if I find the minimum over the space of all possible operators, it gives you exactly this condition. So you could say this is the Euler-Lagrange equation of this action. If I write an action with this, which is quadratic in this O, the Euler-Lagrange equation is this. So I have now a way, which is that if I minimize this object, I can basically find the exact solution. But now we would like to say, well, let's try to minimize this over not all possible operators, but over all the operators that we have access to, all the operators that we care about, all the operators that are relevant, whatever. And so, oh yeah, that was mine. Basically, well, it's not because I found this variational method, right, that I have some Euler-Lagrange equation that, oh, it's good to solve this Euler-Lagrange equation in some restricted way. I mean, we kind of have to say, well, this S, does it have a meaning, you know? Is it, if I'm minimizing this action S, what am I doing something that is sensible? And actually we are. So basically in this paper here, we've shown that if you minimize this action S, it's actually formally equivalent to minimizing the rate at which you are introducing energy fluctuations in the system. So imagine you start in an eigenstate, so the variance of the energy is 0, right? Because you're in an eigenstate, so there's no fluctuations of the energy. Now I try to do my my adiabatic sort of changes, and then I do some counterdiabatic driving as advertised. Now I ask, after doing this procedure, what's the fluctuations in the energy? And yeah, if I succeeded perfectly, then I'm still in an eigenstate, so the fluctuations are 0. Well, and so we can show that the rate at which these fluctuations grow is exactly proportional to the expectation value of this object in an eigenstate. So if you average this over all eigenstates, which is the average rate of increase of the energy fluctuations, that's exactly this object. So minimizing this is just equivalent to making sure that the fluctuations increase the slowest. So that seems like a good thing. Right? So this is what I'm proposing. And you see that this has a lot of nice properties. It's just quadratic in operators, so it's convex. Nice. It's positive, so there's no like saddle points or some things like that. So it's really easy to minimize as long as you use a sensible ansatz for these operators. So okay, let's do an example. I talked about many body systems. We have a bunch of examples of many body systems. If you like to talk about it, maybe just come and talk to me about it after the talk. But I want to introduce this free problem. So there's no many body system here. It's just a free gas, just because I want to show an experiment with it, which I think is neat. So let's imagine we try to control the following system. So we basically have a free particles that can hop on a lattice, and there's some potential that can change with time. And so now, in principle for this, of course, since it's non-interacting, I could work out the exact solution. But let me try to use this variational method that I just proposed. Well, one of the nice things we can try is let's take the most local possible ansatz for this gauge operator. And actually, the most local possible one that obeys all the symmetries that it needs to do is a current operator. So you see that this is C dagger I plus 1, C minus the conjugate times this I. So this is like a current operator, and it can be locally fluctuating. And these alpha are my variational coefficients. And if you go to this procedure that I described, the algebra is not super interesting, but if you trust me, basically to find the optimal coefficients, you have to solve this finite difference equation, which if you coarse grain just becomes some differential equation that you need to solve. And the nice thing is actually that in this particular case, if the potential is linear, so an electric field, for example, this is like a gradient expansion in the operator V. So basically, when I restrict to this local term, actually the corrections that I would get by not doing that are higher order derivatives of the potential. So it's actually exact for a linear potential. So let's say for this linear potential, what it kind of looks like, just to give an idea of what things kind of look like. So what if I want to switch on an electric field on this lattice problem and do exactly as advertised? Namely, I switch on adiabatically this electric field. And now I want to do it super fast without creating excitation. So let's say I change lambda, which is the strength of the electric field, as a function of time according to this dashed line, right? So it's basically, there's no electric field in the beginning, and then I switch on the electric field. It turns out, well, basically here we look at the fidelity as a function of time. And then basically we see that, okay, in the beginning, we're still in the ground state, but then, well, very quickly, basically we become orthogonal to the ground state. And why is that? Well, the original problem was delocalized, right? If I didn't have this electric field, the orbitals are just plane waves. But once I switch on this electric field, the orbitals become stark localized. So I have to go from delocalized orbitals to localized orbitals. And that's, of course, very hard to do adiabatically. Or in other words, there's no gap in this problem. So the fidelity is terrible. And so if I go through my procedure that I just described, actually you can apply, instead of applying this electric field, if you apply this blue electric field, which first basically goes up very high, so it kicks the particle, then sort of goes negative and smoothly ramps back. Well, then the fidelity looks like this blue curve. So basically in the middle of the protocol, it's kind of orthogonal to the instantaneous ground state, but then kind of recovers and gives you like 70% fidelity. So this is, I hope this kind of makes sense. So now we want to use this in an experiment. So why am I explaining it to you? Well, because as I said, I think we did this nice experiment in the group of Dries Gadway. They can make these synthetic lattices of a Bose-Einstein condensate. So basically the system you have to think about is a BEC that is trapped in a trap. And what Dries tries to do is the following thing, which is depicted over here. Now imagine that you have your condensate and you shine two counter-propagating lasers on it. One is this laser omega plus over here, and then there is this retro-reflected laser, which has different frequency components. Why is he doing this? Well, he's doing this because they worked out basically how to cause transitions. So you see omega plus here and omega minus over here. How, if you choose the frequencies of these lasers in a nice way, you can actually have a resonant transition between different momentum states in this condensate. Right, so the condensate is trapped. I shine two counter-propagating lasers. If I choose the frequencies exactly the difference in the energy of this harmonic dispersion of the free particles, well, then I can have resonant transitions, right? Well, essentially this is Bragg spectroscopy, right? And what you are doing like this is basically depending on the laser field, you can sort of, in the beginning, the condensate is static in your lab, right? So the condensate is condensed in the zero momentum state. Then you can switch on the laser. And let's say this yellow laser basically controls the effective hopping strength to go from the zero momentum state to the one momentum state or -1. And then the green laser controls the 0 to 1 and so on and so forth. So basically by having this photon assisted tunneling, let's call it like that, you can control the hopping between the different states. So you have a lattice in momentum space now. But as you can see, the problem, this has nice features because since the hopping is controlled by a laser, means that you can not only just control the amplitude, but you can typically control the phase difference between the two laser fields, which means you can control the phase of this hopping element, which means that you can introduce gauge fields in this lattice system, and they want to do this so they can produce some topological interesting systems. But the problem is you always start in a localized state on this lattice and you have to delocalize it, right? Because if you want to study ground state physics, you basically have to go from this condensate that's condensed in the zero momentum state to a condensate that's delocalized over your entire lattice. And well, basically they had been doing this adiabatically by super slowly switching on the lasers for a very long time. Well, now no surprise that after what I said, you can exactly do what I was saying. Basically, if you change not just the laser fields by slowly switching the lasers on, but you compute what is the counterdiabatic drive, you can actually, and that's what we did. So I went to Dries and I gave them a little computer program that they could use to basically compute how they have to switch the phase of the laser so that they can compensate for all these diabatic transitions. And I mean, there's a lot of plots in here. Don't look at maybe all of them. I think this is a nice one where basically, you see, this is exactly this condensate in momentum space. Initially, it is in this orbital over here, and we're, oh no, sorry. Initially, it is in this orbital over here, and we're in this example trying to move it from here to there. So the target is this red circle, and we start in this black circle over here. And you see, without this counterdiabatic driving, well, it's kind of delocalized over all the lattice sites in between. So it got stuck at the initial position. And then with this counterdiabatic driving, you see that basically we transferred almost all the weight into the target space. And if you look, for example, here at the transfer rate, you see that this is the probability of transferring the atoms as a function of the system size. And so basically you see that if you don't do counterdiabatic driving, this decays very quickly because you see this is a log scale and this is L, so this goes down, I don't know, like maybe not exponentially, but very fast. And with counterdiabatic driving, we basically get 1. So this is super nice because they could speed up their experiment by like an order of magnitude or something. So I really like this experiment. Somehow it's not attracting any attention at all. So that's why I want to show it. I want to kind of revive it. So you see we can do this. Now comes the next thing. I advertised Floquet, so I'm going to do some Floquet. So basically in this experiment by Dries, they have a lot of control in this experiment. So they could literally just engineer this gauge field A in their experiment, right? As I said, on this lattice problem, this gauge field to first order is just a current operator. And since they have control over the phase of their laser, they can just inject current in the system. Now, in many systems, you cannot do this. And so we came up with this procedure of Floquet engineering these unitaries. That's the final piece of the puzzle. So to kind of explain it to you, and this is also a nice experiment done by Alex Sushkov, I want you to consider this Landau-Zener problem. So just consider one qubit. There's a simple like splitting of the energies, and then I can control the transverse field. And it's not hard to compute this counterdiabatic drive. It just becomes something. Oh, I forgot to write. There should be a sigma y here. So basically, it's sigma x. This is the original operator, and then your counterdiabatic drive is this term times sigma y. And so now let's imagine that you cannot control the sigma y field. Maybe you can't, right? So in this case, I can engineer actually a sigma y in a relatively simple way, because I could say, but imagine that I have the following Floquet Hamiltonian, which is just cosine omega t, and then sine omega t times sigma x. So I modulate this. Well, if this frequency omega is much bigger than any of the scales in this problem, then I can just do high frequency expansion. Well, in high frequency expansion, you see the average of this, it drops out, right? Because on average, I mean, this is 0, and on average, this is also 0. So in high frequency expansion, the first term doesn't contribute. So the first interesting term in high frequency, the one that contributes, is actually the commutator of this with this. That will give you a non-zero contribution. Well, but that's exactly sigma y. So basically, to first order, you're going to get, this is the first Bessel function of this coefficient c times sigma y plus all order 1 over omega corrections. And so now you see I've engineered sigma y by Floquet driving x and z. And now we can do exactly that. As I said, this works, but we have a time-dependent h of t, right? And we also have this thing be time-dependent. So now we're just going to use scale separation to say, as long as all of these fields, h of t and lambda or whatever, are changing slowly with respect to this drive frequency omega, well, then in some small period, I can just view the problem as being static, right? And so I statically engineer this Floquet drive. So that's the control parameter, is that basically everything needs to be slow as compared to omega, and then we can do it. And I'll show you in the next slide basically what happens if we have a more complex system than a qubit, but I guess, oh yeah, here's Alex. First, I want to show you the experiment. So again, in the experiment, we did exactly the same as before. You ramp through this Landau-Zener crossing very quickly, and well, you do it with or without counterdiabatic driving. And so the results are the following. So basically, this is the fidelity as a function of time. And so if you ramp just very quickly, you get this purple line. Basically, you get very low fidelity and you get all of these oscillations because you've kicked the system, so it keeps rotating. And if you apply counterdiabatic driving, these two different lines are just two different types of counterdiabatic driving. You can get fidelity 1 in this experiment because basically you're not making any error at all. And so here we show the same. This is during the protocol, but we can now actually vary the time of the protocol and plot the same thing versus time. And so basically what we see here is that if you look first again at the purple line, if you go very fast, then of course, yeah, you're basically dominated by all the diabatic Landau-Zener transitions, so the fidelity is very bad. Well, then you go slower and slower and slower, so it's getting better and better and better and better. Ultimately, you would expect this goes up to 1, but actually it never goes up to 1. It sort of stops around 0.6 and then starts going down. Well, why is that? Well, that's because of decoherence of this qubit, right? This is an experiment. So in this experiment, it turns out that basically if you were to try to adiabatically prepare the state, you can never do it because the Landau-Zener time is like the adiabatic time to prepare it is longer than the decoherence time of this qubit. This yellow line basically is if you directly implement a Y field. Again, this is actually an NV center experiment. So of course you can just apply a magnetic field in the Y direction, which proportional to this. So then you get very high fidelity. But again, because of decoherence, it starts to go down and merges with the Landau-Zener protocol. But the nice thing is that if we actually do this Floquet engineered protocol, we get this blue line. We actually get even much better than the direct engineering of this counterdiabatic drive. And I mean, this was an unexpected byproduct of our efforts. I should say it, right? Yeah, we didn't know this was going to happen when we did it. But actually, in hindsight, it kind of makes sense because actually by applying this high frequency drive, we're doing dynamical decoupling. So it's actually nice. Basically, we're shielding the system from some of the noise by applying a very high frequency tone to the system. So this improvement here is basically due to dynamical decoupling. Okay, so now a few slides, and this is all summarized in this very nice paper with Peter and Mohit and Anatoly. How can we do the same thing in a many body system? And we can do the same thing in a many body system if we do it in a clever way. So basically, again, I'm showing again the same object, the matrix element of this operator A between eigenstates, but now there is a convenient expansion for this operator. There's many expansions possible, but actually a convenient basis for this Floquet engineering is actually if I use the operator basis, which is take the derivative of the Hamiltonian and then take the, well, kth order nested commutator with the actual Hamiltonian. If you keep doing this forever, it forms a complete basis for this operator. It's basically the perturbative expansion of this operator A. So why is this convenient? Well, the idea is basically just that we're gonna use this operator as a basis and use this variational principle to find the coefficients. And well, I'm trying to convey here, actually finding these coefficients is nothing but in this basis, you see that I can take all these matrix elements with the Hamiltonian because they're all eigenvectors. I mean, M and M are eigenvectors of H. So I basically just get the 2k minus 1 power of this EM minus EN. But the exact answer is 1 over EM minus EN, right? So basically, you're doing a Taylor expansion of 1 over X in powers of X. Seems very bad to do. It's also not a great thing to do. But the point is that you have matrix elements of this operator here, which basically means that you only have to fit 1 over X in the window where the matrix elements between these things are sizable. So that's what this is doing, you see. By putting higher orders, we're fitting 1 over X in the relevant window where the matrix elements contribute. But if we do it like that, which is not the best basis for this convergence, as you can imagine, but it is a good basis for Floquet engineering, because some of you might have already realized that, well, these terms, all the nested ordered commutators with the Hamiltonian, well, they're exactly the terms that appear in the high frequency expansion of the Magnus Hamiltonian, right? So if I write down Magnus series for the high frequency Hamiltonian, Floquet Hamiltonian, I get exactly these terms. So since I'm not a super clever person, but this I can do, you know, it's like I get the same type of perturbation series than this series. So then at the end of the day, I can just match the coefficients order by order, right? I solve for my variational coefficients. I do my Magnus expansion, and then I just match them. Oh, then I just match them sort of one by one. And okay, I had one last slide, but somehow this is not showing up. So I guess, so this matching order by order in a many body system actually works very well. And so we could use exactly the same trick as here. Basically, instead of having the bare Hamiltonian over here and this counterdiabatic drive, by periodically modulating this Hamiltonian and periodically modulating this field, we generate a Magnus expansion of this and match all the coefficients to this counterdiabatic drive. And we can get orders of magnitude increase of the fidelity of our system. And now you might also basically see what the reason, because now you see this sounds like a free lunch kind of thing. No, it's like just have to do like some periodic modulation and then I can control my system. Well, the point is that actually if you go through this procedure for every order in the Magnus expansion, because you want to control the individual terms independently, that means that if you want to go one order higher, you need to introduce one more harmonic in your drive, right? So for every term you wanna control, you need to add a harmonic to your drive. So what is the resource that you're using to do this counterdiabatic driving? Well, it's the bandwidth of your laser, right? So basically, in this way, that physically, that's what I kind of like about it a lot, is that it immediately shows you that even if you could find all these coefficients sort of perfectly and do everything, the quantum control problem or the resources that you're using is just a bandwidth of the classical system that you're using to control the quantum system. If you have a bigger bandwidth system, you can do the control better, right? But if the bandwidth of your system is limited, then at least in this way, it immediately shows you that your control will be limited. So now one of the things we're of course asking is that, well, with a given fixed bandwidth, the number of harmonics that I can apply is fixed. So how good of a control can I do, right? And so let me stop here. So basically, I hope I convinced you of the following message, sort of that optimal control of quantum systems is important these days. And that actually you can, instead of doing some brute force numerical methods, you can split the problem into two subproblems. One problem is finding these adiabatic gauge connections. The other is engineering these out of the available controls, right? One way to engineer them is by this Floquet engineering, which I've just explained. And then the way we can find these gauge potentials without diagonalizing the Hamiltonian is by using this variational principle. And then the things we're currently working on is that, of course, we need to find, or at least that would be nice if we can find sort of a better ansatz for this gauge potential. So I use these commutators, but that's only one thing to do. Currently, we have nice work that I think will come out soon on tensor networks. So basically, we use matrix product operators to find these gauge potentials. Now we need to find better ways to engineer these unitaries. And you see, once I have a tensor network for this AGP, then I can start thinking of making a short depth. Well, because there is an immediate link between a tensor network and a short depth quantum circuit, I can make a short depth quantum circuit that engineers this MPO. So that's stuff I think that will come out soon. So that was it.
Thank you very much. So there's time for questions. Perhaps we'll start. Are there any questions from students or postdocs before opening for everyone, including people online? So I think I can see here if there are questions online. Volunteers, students. So questions from anyone? Yeah. So 2 rows back.
Yeah, it's working. Dries, for the nice talk. Yeah, so in this construction of the AGP, the adiabatic gauge potential, you're trying to transport the entire spectrum. Mm-hmm. And do you have a formulation in which you're just transporting like the low energy spectrum?
Yeah. Basically, it's very simple to show that if you replace this trace by a projector on any subspace, that you find the exact solution on that space. So if you want to, for example, only transport the ground state, basically you only need to care about matrix elements with the ground state. So you can put a projector here on the ground state, but if you plug that all in, it just becomes a projector here on the ground state.
I see.
And so maybe to add to that question actually is that, which I should have maybe said, is that as long as, for example, you only care about the ground state or any other state and the system is gapped, then you can show that this operator A is local, like with
Great.
exponentially decaying support.
Thank you.
Thanks for a nice talk. It was very good. I was curious about the first part of your talk where you introduced this motivated by efficiency.
Ah, yeah.
So here you've now introduced some perturbation that presumably does some work. So is there some kind of competition to revisit the efficiency of quantum processes?
Yeah, we have been doing that as well, actually, because, you know, there's this, what's it named again? Calvo-Alzon bound, which basically take a classical engine. We all know about the Carnot efficiency, right? But you can also ask, what is the efficiency at maximal power, right? And there's a bound actually in the case of classical systems that at maximal power, the efficiency is much lower than the Carnot efficiency and something like square root or something of that. And many people sort of believe that this is a fundamental sort of theorem that the efficiency at maximal power cannot be higher because, yeah, you are producing power. Actually, by this counterdiabetic driving, we have shown on some quantum engine simple problems that you can get arbitrary high efficiency. Like you can get, well, arbitrary high, no, you can get Carnot efficiency at finite power and ultimately at any power you want. Of course, now you can ask how much resources am I using? And yeah, you are of course doing work by having this lambda dot and term, but actually you do as much as you re-extract later if you do it in a cycle. So yeah, you can get Carnot at finite power if you do this.
Can you go back to the slide to the fermion chain where you show the fidelities?
Yeah.
Right. So the one on the right hand side here. So the blue curve, which is the counterdiabetic one. So when you lose the fidelity, did you look at the participation ratio or the diagonal entropy? Like, does your state delocalize over the entire eigenbasis, or do you go into just another eigenstate?
So yeah, roughly. So what's happening here is exactly that. It's a good point. So I didn't stress it here, is that if we were to apply exactly this counterdiabetic drive, then of course the fidelity with the instantaneous ground state should always be high, right? So here it's going down to 0, and actually this is like some really tiny number because this is the many body fidelity of this free fermion chain. So it's exponentially tiny in the number of fermions. Why is this happening? Well, again, because I'm actually doing this additional gauge transformation. So in this gauged frame, I'm not actually having high overlap with the instantaneous state. So it's this example of the glasses again, you know, it's that basically if I apply the field, so the gravitational field to compensate for the pseudo force, clearly the situation where my glasses are tilted is not the equilibrium state, right? This has low overlap with the equilibrium state. And so here, yeah, it's delocalized. The fidelity is exponentially tiny. So it's delocalized over many, many, many states. But of course, a particular set of them.
Other questions?
Okay. Yeah, I have a question about the free fermion chain. So could you go back one slide? And even if the your potential is not linear in I, it's still kind of solvable easy, right? Because it's a linear equation for alpha.
Yeah, exactly. So this basically you can always solve, and this is always an approximate solution, even if the potential is not linear. When the potential is not linear, there's just the exact, I mean, this is free fermions, right?
Yeah.
So the exact potential is also a two-body term, but it contains in this language multi-hopping, like next nearest neighbor terms. So you see, the only approximation that I do here is that the full gauge potential is not just nearest neighbor, but next nearest neighbor and next nearest neighbor. So if we truncate that, then this is the solution for only the nearest neighbor term. And yeah, you can solve this always, right? I mean, you can write down the Green's function of this and solve it, but it's still not the exact solution when the potential is not linear, just because then there's next nearest neighbor terms that are non-zero. For the linear potential, it turns out that the fact that this becomes really easy to solve because the Green's function is really easy also comes with the fact that the next nearest term, nearest neighbor terms are exactly zero. They vanish.
Okay, thank you.
So, on this slide, so you have this, if V is a disordered potential, then this A will decay as you go away further and further away. So it just like looks like a local integral of motion that you are generating.
Exactly. Yeah, that's basically the idea. Yeah.
Okay. So it's like a locator expansion for it.
Yeah, exactly. And that's the thing. We've actually been applying it also on some just sort of nonlinear field theories and finding like new local integrals of motion. So yeah, there is a clear connection.
Okay, thank you.
I had a question. In one of your examples, you showed that when you had the system with dissipation, that you saw that, oops, that's not on. Okay, you have to be close. Okay, so you showed that with one of the examples, when you had dissipation, you found that the flow case system actually took away the dissipation. Have you tried approaches where you deliberately try to engineer the flow case accounting for dissipation and trying to minimize its effect as well?
No, but it is a good idea. So after doing this, that's exactly what we sort of thought about, is that actually you can take counterdiabetic driving to the next level, which is to say, well, what if I have a general CPTP map, like some dissipative quantum channel? I can still try to apply all the same ideas, but then I should get gauge potentials which also care about the actual dissipation in the problem. And that is something we have not done. And as far as I know, it actually has not been done by anyone, but it's a great idea.
Okay.
So now it should be fast because this is on Zoom or on YouTube.
Okay, any other last questions? Any online? No? Okay, well, let's thank Dries again for an excellent talk.
Thank you.